In the last episode, we built one shared informer. It receives pod changes, updates a shared cache, and tells local handlers that something has changed. But those changes may arrive much faster than a controller can finish its work. So where do the changes wait? And how does Kubernetes stop one busy pod from overwhelming the controller? A useful way to picture this is a mailroom and a task board. The mailroom receives every new message and keeps related messages together. The task board does something different. It only reminds a worker which customer still needs attention. Kubernetes uses the same separation. DeltaFIFO handles incoming changes, while the work queue schedules controller work. Let us follow one pod, default/pod A. It is first created at resource version 501. Before the controller gets a chance to react, the pod is scheduled at version 503 and becomes ready at version 504. 3 changes have arrived, but they all belong to the same pod. Kubernetes needs a stable name for this pod, while the pod itself keeps changing. That name is the object key. For a namespaced object, the key is usually the namespace followed by the object name. Every one of these events therefore maps to the same key, default/pod A. Now, think of a very important concept here that justifies why a simple event queue is not enough. Imagine pod A is created and then updated twice. Each of those changes is an event. From an informer perspective, the informer needs those events so it can update its cache correctly. But the controller does not need every event. It only needs one reminder that pod A should be checked. That is why Kubernetes keeps the event queue and the work queue separate. Kubernetes handles this in 2 clear steps. First, imagine pod A is created and then updated twice. These changes arrive at DeltaFIFO, which keeps them in the correct order. The informer processes those changes and updates the shared cache with the latest state of pod A. Once the cache is updated, the event handler does not send all those changes to the controller. It simply adds the key, default/pod A, to the work queue. A worker then picks up that key, reads the latest pod A from the cache, and decides what action is needed. So DeltaFIFO helps update the cache correctly, while the work queue helps the controller decide what to work on next. DeltaFIFO has 2 connected views. The FIFO tells us which object key reached the waiting line first. Behind each key is a bucket of deltas, meaning the ordered changes that arrive for that object. The key appears once in the FIFO, while its bucket may contain several changes. Now let's imagine pod A changes again while it is still waiting. DeltaFIFO does not add a second pod A key to the FIFO. It appends the new delta to pod A's existing bucket. This preserves the change history needed by the informer without filling the key queue with repeated copies of the same object. Here's an important point to remember. DeltaFIFO never ignores the changes that happen while a pod, say pod A, is waiting. If the pod is created and then updated twice, those changes are kept in the same order. DeltaFIFO groups them together for pod A until the informer processes them. It may remove repeated delete messages when they no longer add anything useful. So its main job is to keep related changes together, not to throw the history away. When pod A reaches the front, the informer pops its deltas as one unit. It processes the oldest delta first and the newest delta last. Those changes move the shared indexer from its earlier state to the newest known pod A state. Only after the store is updated are local handlers notified. Deletion needs extra care. Sometimes a delete notification can arrive after the object has already disappeared from the local store and the full pod information may no longer be available. Kubernetes still keeps the pod's basic identity, such as its namespace and name. This allows the controller to understand which pod was removed and take the right action. So DeltaFIFO belongs to the informer, not to the controller worker. It answers, what changed for this object while it was waiting to update the shared store? Once those deltas are processed, the informer can notify handlers using the new cached state. After the indexer is updated, an event handler is called. The handler normally does not place the complete pod or its entire event history into the controller's work queue. It adds the object key. That key is a simple reminder. Default/pod A may need another reconciliation. Suppose pod A changes 3 more times before a worker picks it up. The handler tries to add the same key 3 times. The work queue keeps one pending copy. That is safe because the worker will not replay old events. It will read the latest pod A state from the shared cache. The work queue keeps a list of objects that still need attention. The worker asks the queue for the next item by calling get. The queue then gives it the key for pod A, which is default/pod A. This key only tells the worker which pod to check. It does not contain the pod itself. The worker uses the key to read the latest pod A information from the shared cache. It compares the current state with the desired state and takes any action that is needed. Once this check is complete, the worker calls done to tell the queue that it has finished processing pod A for now. Now imagine pod A changes while the worker is already processing it. The work queue does not run a second worker for the same key at the same time. Instead, it marks pod A as dirty. When the first worker calls done, the queue adds pod A back once, so the new state gets another reconciliation pass. This gives the work queue an important property. The same key is processed by only one worker at a time, but different keys can still be handled in parallel. One worker may reconcile pod A while another works on pod B, without allowing 2 workers to race over pod A. Reconciliation can still fail. Perhaps the API server is temporarily busy or another dependency is not ready. Immediately retrying in a tight loop would make the problem worse. A rate-limiting work queue waits before adding the key again, usually waiting longer after repeated failures. When reconciliation succeeds, the worker clears the retry history by calling forget. Done and forget have different jobs. Done tells the queue that this processing pass is finished. Forget tells the rate limiter to stop remembering earlier failures. DeltaFIFO and the work queue are both queues, but they remember different things. DeltaFIFO remembers the pending changes needed to update the shared store. The work queue remembers which object keys still need controller attention. One protects the flow of observed state. The other protects the flow of work. Here is the complete journey. A watch event reaches the reflector. DeltaFIFO groups the object's pending changes. The informer updates the indexer and notifies an event handler. The handler adds the object key to the work queue. A worker takes the key, reads the latest cached state, and runs reconciliation. A controller does not need a separate instruction for every change. It only needs to know that an object may need to be checked again. So the work queue can send the same pod key more than once. Each time, the controller reads the latest state and decides what needs to be done. But how can it safely repeat the same check again and again?